G'day guys, Mr. Bennett here. Hopefully you enjoyed the last two videos that gave you a bit of an introduction to this topic. So the first one being on astronomy of light. So obviously in astronomy, analysing light's a really important part of that. So we'll be looking at the atomic absorption spectrum and also the line emission spectrum. And so part of the theory, what we want to do is explain how that works and why it occurs. And then the other one, which is an introductory video to history of the atom. Alright, so I'm going to start from basically what we are going to consider our model of the atom. So our model of the atom is we're going to have a nucleus. Okay, inside of our nucleus we're going to have positive charges and we're going to have zero charges as well. Okay, and then we have electron shells. Alright, so these electron shells allow electrons to orbit at fixed orbits. And there'll be multiple shells and they have fixed energy levels, so the concept is that the electrons will move between these different shells, but also they obviously want to be closest to the positive nucleus. Right, so in here we have our electrons buzzing around and we'll have 2 in the first shell and then we have I think it's 8 in the second shell and so on. Right, but you've got electrons there. Now electrons can move, as we've seen when we start looking in X-rays. If an electron sort of went missing from there, what would happen is that electron would drop back down there. And if this electron went missing, then that electron there would drop down from there, and so on. Alright, so that's the concept of the atom itself. Now, give you a perspective of the size of the atom, then if we were thinking about a football oval, right, so like our town oval, so we'll get our football oval there. If we have a pea, that's the size of a pea, inside of in the middle of the oval, then the first electron shell, the electron shell was basically running around the boundary line. Okay, so that gives you a representation of the size of the nucleus in comparison to the size of the atom itself. So we know the nucleus has a couple of things. The nucleus has all of the mass, pretty well all of the mass, and it's very tiny. I always love telling people that, you know, obviously when you start looking at an atom, well, an atom is basically 99% space. Alright, so if you're thinking about 99% space and you're thinking of an atom itself, well, we're made up of atoms. So if you want to tell someone they're about 99% space, then that's true. Alright, so even the fact that you might think atoms are quite dense and all of that, but you know, literally they are pretty well made up of mostly space. Right, so the interesting experiment, I think is a really important one, was the one where we had the alpha particles fired at a very, very small thin gold foil. Okay, and 1 in 10,000 of these particular alpha particles, when it went into the gold foil, bounced back. All right, and the analogy was used that this was like firing a 14-inch shell into tissue paper and getting it to rebound. So this led to the idea that rather than Rutherford's plum pudding model, that there must be, J.J. Thomson's, was it plum pudding model? Yeah. All right. So rather than having the plum pudding model, what we've got here is we've got the concept of the alpha particle hitting a very massive particle or section of the atom itself, which is the nucleus. All right. So all of the nucleus is made up of protons. All right. So the nucleus is made up of protons and neutrons. Alright, so and they have all the mass. Alright, so they've got all the mass associated with it. Electrons are very light compared to all of these things. They do have a little bit of mass, but it's negligible when you compare it to that. And obviously we have electrons. Alright, so that's the essential model that we need to work with in terms of the atom itself. So we have these electrons in fixed shells, and we have a nucleus which has all the mass. Now the question is, how do we know about these electron shells? Obviously there was some theory that related to that, And this is what we need to understand, is that there is a theory related to that. So I'm going to draw the electron shells. I'm going to draw them slightly differently. Here, if we're thinking about atoms themselves, this is the ionization energy. So the ionization energy is the energy that's required to eject an electron outside of the atom itself. Alright, so that will liberate the electron. And so there's going to be a series of electron shells, and I'm just going to draw some of them. Okay, so we'll say this one here is the ground state. So the ground state is where it's most stable. Considering here, if we're looking at this cell here, this is where the nucleus is. Right? The nucleus is down here. So electrons want to be in the most stable state, which is the ground state. Okay, and then our first excited state, second excited state, third excited state, and so on. Okay, so we'd say this is our energy shell 0, E1, E2, E3, and so on. So when we're looking at light itself, we know that electrons will do what? Well, electrons want to be in this state here. When we start looking at very simple atoms like hydrogen was the one that was used, well, it was seen that when an electron goes from there down to here, what's going to happen, the theory is you'll eject a bundle of energy, which we call a photon. So these photons will have energy that associates with the energy levels between these shells. So if I have an electron falling from there to there, it's going to have a set amount of energy corresponding to that particular thing here. And then obviously going down there, it could fall from there, but it could also, from that one there, it could also fall directly. The electron could fall straight to the ground state as well. So, and there it could fall from here, and it could fall down to there. It could also fall straightly down to the ground state there as well. All right, get the idea? So particularly when we start looking at electrons or atoms, they're going to have set shells or set energy levels that are going to correspond to where electrons move from a higher state to a ground state or to a less excited state. And so when we start looking at the theory and observations in real life, if we start looking at our line emission spectrum, we get a black background, and then we'll get particular lines that correspond to these particular things over here. So these energies correspond to the particular energies between the electron shells. All right. So, and what's been done is if you excite these particular atoms, like it's pretty easy when you start looking at hydrogen. What you can do is just burn it, excite it. So you excite all the electrons, and you can look at the light coming from that, and you'll get all of these particular lines that correspond to the energy gaps between these things here. All right, remembering from what we learned in our previous topic, energy is equal to H times by that, which is equal to Hc all over the wavelength there. All right, so the frequency of the light or the frequency of the photons coming off give you a guide to how much energy the photons actually have, and so there where they will actually fit across that spectrum. So if when we start looking at, this is a small part of the visible light spectrum, this is what we're looking at here. Anyway, I'm going to leave the video here. I'm going to talk about that in a bit more detail in our next video.